Hello everyone, the teen engineer here, and today we're going to be tackling another linear momentum problem. So let's read it. A block of mass 2.3 kilograms is attached to a massless spring. A projectile of mass 178 grams approaching the block horizontally with a speed of 170 meters per second from the left embeds itself in the block upon striking it. With what speed does the block recoil from its rest position, and when the block has recoiled as far to the right as it will, what is the potential energy stored in the spring? So to begin, I'm going to designate different points in time. So we have point A, we have point B, and we have point C. So point A is when the bullet is just traveling through the air. Point B is right at the point of collision. And point C is when the block has recoiled as far as it can. So, with what speed does the block recoil from its rest position? What this means is what is the speed of everything at point B, because the bullet is going to embed itself. So, what's the speed of everything at point B? So, let's tackle that. So, we're going to start with the linear momentum formula, conservation of linear momentum. Initial momentum is equal to final momentum. So initial momentum is just the momentum of the bullet, because that's the only thing that's moving, and the bullet is 178 grams, so that's 0. Well, first off, I'm just gonna write it like this. So bullet times velocity of bullet is equal to mass of total, because it's the block plus the bullet, times velocity, which we're trying to find. So let's replace. So 0.178 kilograms times, that would be 107 meters per second, is equal to total mass. So the total mass is 2.3 plus 0.178. So 2.3 plus 0.178, and that's 2.478. 2.478 kilograms times VF. So now all we have to do is just multiply and divide. 478. That would be 7.69. So 7.69 meters per second. So let's have a look if that's the answer, which it should be. Good. Now, when the block has recoiled as far to the right as it will, what is the potential energy stored in the spring? So they're asking us, what is the potential energy at C? Now, what we can do here is use the conservation of energy theorem from B to C, not from A to C, because this is an inelastic collision. So delta K is not equal to 0. So there was energy that was lost. But from B to C we can, since the impact has already happened. So whatever energy we have at B is going to be equal to whatever energy we have at C. So first off, let's calculate what energy we have at B. All that we have at B is velocity. So with velocity, it means we have kinetic energy. So let's calculate that. So first, I'm just going to make different colors for, let's say this is going to be, B is going to be yellow, and C is going to be purple. So energy at B is just kinetic energy. So, and that's equal to 1/2 m total V squared. And then we can just replace times, and then total, it would be 2.478 kilograms times 7.69 meters per second squared. So let's do that. 1/2 times 2.478 times 7.69 squared, which would be 73.27. 27 joules. And since we can use the conservation of energy theorem, energy initial is equal to energy final, so this would allow us to say that energy at B is equal to energy at C, which means that all the kinetic energy which was at B, all of it is going to be transferred into the potential energy of the spring. So as the spring compresses, the kinetic energy is gradually giving all of its energy into the potential energy. So it's being converted. So it's going to be 73.27 joules is going to be equal to energy at C. And that's basically all we need to do. Since everything at C is just potential energy, this kind of answers the question. So let's have a look. And yeah, that's it. So that's how you solve this problem. If you guys like this video, then give it a thumbs up, subscribe, and I'll see you guys later.